the second section, which we call the electromigration. So what's the electromigration? Actually, we are going to talk about the mass transport under electrical field. So yes, you did apply the electrical field on your materials, and that will cause some mass transport. So we are going to divide it into two different categories based on different material system. For the first one, we are going to talk about would be the charged ions in ionic conductors, in ionic materials. And the second category will be we apply the electrical field on the metals. And that will be the different story. So let's move to the details. And we will move to the details in the following slide. And before we end the electromigration, we are going to show you there are two case studies to well describe the effect of electromigration. And first one we call it the short strip effect, and the second one is we call it the current clouding effect. So this effect actually you can observe the vacancy formation in your materials, and in real cases in the IC chip, especially you can observe this in the connecting wire. So if this happens, then there will be effect reliability of silicon chip, a silicon-based chip, the IC chip. So because as long as the void gets larger and larger, then when it covers the whole conducting line in your chip, then they will fail the chip, right? So that's why these two effects, this case is quite important, and that's the reason why we introduce electromigration in these lectures. Let's move to the first category. When you apply electrical field on the ionic materials, and in these ionic materials that contain a dilute concentration of positive charge ions that diffuse interstitially. So, for example, like you have an ionic material ZnS, and within this ionic material, there's a dilute concentration of copper positive charge ion, and this ion locate at interstitial site and also diffuse through interstitial sites. So we call it this diffuse interstitially. And we apply an electrical field on these materials. Can you just try to write down the driving forces apply on this ionic material? So as we know, the driving forces can be expressed like the potential gradient minus potential gradient. And in this case, the potential of this interstitial ions can be expressed like the first term is a chemical potential gradient. This term is due to the concentration of these copper ions, the concentration variation of these copper ions. And the second term actually comes from because we apply an electrical field on these materials, as long as these ions moves through this material interstitially, and these charged ions will cause a potential change, and how much the potential change will be equals to the charge carried on this ion and the potential applied on this system. So based on previous, we can simply formulate the electrical force acting on these ionic ions as the charge it carried, and also times the electrical field we apply on it. Or you can times the Q and potential gradient minus potential gradients appear. So as long as you take this is a potential, so people will when you try to formulate the potential of this charged ion in ionic system, you need to modify the potential, and some people will call it as for example, we'll call it is electrochemical potential. Based on this term, you know that this potential need to be modified. And in the electrochemical potential, when you have mass transport happen in the ionic system, and mass transport means the concentration of ion changes, right? Because diffusion happens, so there's a mass transport of these positive ions. And during this mass transport, the change of the charge dq can be expressed like a dq1 times dc1. Q1 is the charge carried on these ions, diffusing ions, and dc1 is the change of the concentration of these diffusing ions. So we need to submention all the potential energy acting on these interstitial positive ions. If there's no electrical field apply on this material, so when you write down the potential properly, potential energy can be expressed like a mu1 dc1. But however, there's an electrical field apply on the system, right? So when there's one ions move through this electrical field, you need to end this extra turn to modify the potential energy of this diffusing ions. It's a phi dq. The dq is the change of the total change of the charge times the phi is the potential, electrical potential acting on these materials. So dq will substitute by q1 c1, then you just put the dc1 out, then you got this term. So when this is the modified chemical potential term. So you take the minus gradient of potential term, you got the driving force. So for the ionic system, and also you apply an electrical field on it. So the electrochemical potential included the chemical potential term mu and the electrical work phi, and this is you apply on the system. So now the potential of the positive ions be modified as this one included the chemical potential and the electrical work. Okay, so now you know the driving force be driven by the chemical potential, the concentration gradient, or the electrical field you apply on it can be formulated like this. Then you can simply write down the flux of interstitial. That means, for example, like here is the flux of these copper ions can be write down as the first term is due to the concentration gradient or chemical potential gradient is a fixed first law. And the second term is is due to the electrical work we apply on this system. So write down as the mobility, concentration, and also the driving force here. Force will be the charge times the minus potential electrical potential gradient, right? So it's a charge Q1 is a charge carry on this copper ion, and the potential gradient, electrical potential gradient minus electrical potential gradient. So if we assume within your materials there's no significant concentration gradient of this positive copper ion, so we can drop this term out. So now you got the flux of copper ion be expressed like this. This is the how many copper ions passing through unit area in unit time period, right? Is the numbers of copper ions. If you times the charge, that will get the electrical current density. So we use this J1 is the flux of interstitials times the charge. This interstitial atom carried, then you can get the current density. So we direct times the Q1 with this term, you will get this, and current density needs to obey the Ohm's law. So you compare these two terms, you get the electrical conductivity of this ionic material will be proportional to the diffusivity of this copper ion diffused through this matrix, and concentration of this copper ion, and also the charge of these interstitial ions. So for these results will be benefit to the people who deal with or studying with the ionic conductor electrolytes in a battery. Some people use the this ionic material serving as a solid electrolytes in battery. And as you know, the most people want to increase the performance of electrolyte would be try to increase the conductivity. So based on this result, you can expect it if you want to increase the conductivity of this electrolyte or this ionic material, either you can increase the diffusivity of these interstitial ions moves through your material. So some people will deal with the crystal structure of this ionic material. Or some people will try to play with something to which can affect the diffusivity of these copper ions. Or you can change or increase the this concentration of these interstitial ions and the charge also. You can instead of double the copper ion, you can choose other ion with higher charge, carry higher charge, and you also can increase the electrical conductivity. Okay, so this is when you apply an electrical field on ionic conductor and doped with dilute concentration of positive charge. Then next we are going to move to the second category is how about if you apply the electrical field on the metal? The difference between ionic materials and the metal would be is the current density. The current density you get from the metal would be the electrons flow, right? Electrons. So the carrier will be the electrons. So so when you talk about applying a electric field on metals, this is we call the electromigration. You apply an electrical potential gradient or electrical field, and this electrical field induces a diffusion in metals. And due to what? Due to the cross effect between the diffusion species and the flux of electrons. So, for example, like these gray circles are the metal atoms. When we try to apply an electrical field, and we connect a cathode here and an anode to form a circle, and this electrical field will drive an electron flow toward this direction, right? So there are lots of electrons hit or bombard on these positive metal ions. Most of them were reflected and deliver the momentum to this positive metal ion. And this momentum exchange, as long as this momentum exchange get higher, then that will push these metal ions move through these materials. This phenomenon, we call it is electromigration, is the electrical potential and induce the mass transport, the metal ion transport, right? And due to what? The electrons flow, because the bombardment between the electrons and the metal ions. So why is electromigration so important? And when it happens, as you expected, as long as this flux is high enough, then that will happen. So usually only happen in higher, the system exists a higher current density. So people usually observe that in our IC chip, IC design. This is a cross-section of our IC chip. After etching the dielectric material, and you can observe the conducting line, copper, and a constant. If you cut a cross-section and investigate the microstructure of this conducting line, and I remark the direction of electrons flow, you can observe some interesting stuff. Is you can observe some void at the interface, and also there's a large void exists in the conducting line. As long as this void gets larger and larger to cover whole this conducting line, then that will result in the open or the failure of this IC chip. So this effect, electromigration, is related to the reliability of the IC chip. Especially as you know, the microelectric device, as long as the line width decreases, the current density significantly, dramatically increase. As long as this driving force increase, that will this current density increase, that will push more atoms, that will cause the mass transport in your metal materials. And you also accompany a void form within your conducting line, right? So that's why this electromigration is so important. Okay, so let's try to quantitatively calculate the effect of this when you apply an electrical field on the metal. So also we consider what we have here is we have a metal, and this metal be doped with dilute concentration of interstitial atoms. So this is FCC metal, and we dope there's a dilute interstitial atom exists in this metal. Then you apply an electrical field at constant temperature. What happens? The first one is you need to identify how many driving forces exist in the system. To me, is you can simply write down the current density, J small sub e, and Ji is the atomic flux, right? And the driving force, there are two possible driving forces. The first one is concentration gradient, and the second one is the electrical field you apply on it. So the current density directly driven by electrical field times the direct coefficient. And possible driving force is a concentration gradient or chemical potential minus chemical potential gradient, and it times the coupling term. And for the atomic flux one, directly driven by minus chemical potential gradient times the direct coefficient plus it also be affected by indirect driving forces, electrical field times the coupling coefficient. And the current density part is always obey the Ohm's law. And this current density, actually, we are not interested in this one because we are more focused on mass transport. So we need to decouple or get what's the atomic flux, interstitial atomic flux here. So here, there's the atomic flux can be divided into these two terms. The first term is due to the concentration gradient. The second term is due to the electrical field, or the cross effect between the electrical field and the diffusing interstitial atom. So in order to get this term, you can write down this term as a J1E is the atomic flux due to the electrical field we apply on it. So can be equals to mobility of this interstitial atom, concentration of this interstitial atom. Yes, you know, you dope it, so you can use EPMA or EDEX to know the concentration of this interstitial atom and the driving force. So how to formulate the driving force acting on this interstitial atom? Why these interstitial atoms moves through this material is due to the electrons bombardment or electrons flow, right? So we use the beta E to represent the driving force. And the beta, people call it is the effective charge of diffusing atom. And some people, if you check some published articles, some people will probably use the Z star times E to represent the beta, the value of a beta. And what's the Z? Z can be divided into two parts. Is the relative effective charge in static electrical field plus the effect from the electron winds. So the value for beta is some kind is because this diffusing interstitial atom be pushed by electron, right? So it moves relative to how much electrons moves. How much electrons moves. Okay, so usually the value for beta will be negative. Negative implying that the direction of this, the moving direction of these interstitial atoms. Negative means is in the same direction with the electron flow. Okay, so now you get the value for this term, right? So you just use this term so you can get the interstitial atomic flux can be rewritten as the first term is due to the concentration gradient, so you can use the fixed first law to substitute it. Then the second term is this term, we just substitute it. And by the way, some people want to decouple what's the coupling term, LO1Q. Compare these two relationship, you can get this coupling coefficient is related, associated with the diffusivity of this interstitial atom and concentration, also the beta effective charge of these interstitial atoms. Okay, so if this is dilute solution of interstitial atom, that just you just adopt very tiny amount of interstitial atom, so we can make some assumption. If the concentration of this interstitial atom is quite small, you can drop this term out, then you can easily get the atomic flux of these interstitial atoms. Okay, so next slide is going to show you how to determine or measure the beta. So how to measure the effective charge beta? So let's give you an example here. We assume we have a metal materials and inside this material, the concentration of these interstitial atoms is uniform along these materials. And next, what we are going to do is apply an electrical field on this material. So the direction will be go to the left-handed side. So you try to plot the potential versus the location. You can get the will be this direction, right? It's a cathode, it's an anode, and due to this electrical field, you can write down the direction of the electrons flow. So this electrons flow is going to push the atoms move toward the right-handed side. So the concentration profile of this interstitial atoms will become to this. because the electrons push the atoms move toward to right-hand side. But some people ask, oh, after very like a long time period, does the slope of this profile get higher and higher? No. Because as long as there's a variation in concentration of this interstitial diffusing atoms, less the other flux will compensate this effect, we call the concentration gradient. So will be provided the opposite direction of flux. Right? So in the beginning, there's no concentration gradient. As long as you apply an electrical field, they will cause some slightly difference or some variation in concentration, and that will increase. That will cause this flux toward to left-handed side. So as long as this reach the quasi-steady state, that means the net flux equals to 0. That also means this concentration profile do not change over time. Then you can get the value of beta effective charge, because you can use the EPMA node to understand the concentration gradient and the electrical field you apply, as you know. So you can simply get the value for this effective charge of beta. So some people will ask, what's a quasi-steady state? Quasi-steady state, that means it's near steady state. That means during the measurement time, reasonable measurement time probably is 1 day or 2 days, then you did not observe any concentration change along the profile is like this, do not change over time. Then that time period we call it is a quasi-steady state, because steady state means for very, very long time, right? Because we don't have enough time to wait until 1 or 2 years, just want to measure the concentration profile, just want to confirm whether this concentration profile change with location. So during a reasonable time period, then you find that your sample, you plot the concentration profile as a function of location, then you find there's no big change over time. Then we can call that as a quasi-steady state and use the relative parameters, and you can get the value of beta. Okay, so this is how we determine the beta. Okay, so this is when you apply an electrical field on the metal material, and this electron and the electron's flow will push the interstitial atoms moves and transport through your materials. And how about the other case is if we talk about the pure material, and the atoms we talk about is not an interstitial diffusing atom, would be the substitutional atoms. As you know, the pure metals, that means there's only 2 components in pure metals. The one is the atoms at substitutional side, and the other one is the vacancy, right? So how these atoms at the substitutional side diffuse through your sample is by exchanging with the vacancy. So the diffusion occurs by the exchange of the atoms and the vacancy. So if you want to write down the flux of vacancy, can be equals to due to the concentration gradient of vacancy and also the electrical field you apply on this system. And based on the net flux equals to 0, so you can write down the JA plus JB equals to 0. And also, because usually samples exist lots of vacant, the dislocation, the lots of imperfection size, including the point defect, dislocation, or grain boundary, lots of imperfection size, and this can serve as a vacancy sink. So as long as there's a vacancy be generated, and it will be absorbed by the crystal imperfection sign. So we can make this assumption: the concentration vacancy along your material is uniform. So if you drop this term uniform, that means no flux, right? Because there's no concentration variation or vacancy. So this you can drop this term out. So in order to know the atomic flux at the substitutional site, you can write down as a minus JV, and the vacancy fluxes comes from the electrical field you apply on the system. So you can write down as a mobility of vacancy, concentration of vacancy, and driving force acting on the system. So mobility can be expressed like, so mobility can be diffusivity over kT, and concentration. Driving force here is, we call it beta VE. The beta V here is a vacancy, effective charge of vacancy. Usually is larger than 0, right? It's larger than 0. So for metal stuff, as we mentioned, effective charge for metal usually is negative. Negative implying that what? The direction of diffusing atoms move in the same direction with electrons. And the same concept, if positive, that means the vacancy moves is the opposite direction of the electrons. And also, if this is positive, this is negative, and E, right? So you can expect the atoms where the atoms pushed in the opposite direction of electrical field, right? It's a minus E. It's the opposite direction of electrical field, and it will be the same direction with the electron flow. Okay. So let's make a summary for electrical field part. In addition to ionic material, if you put more efforts on the metal part, you need to separate into these two sections. The first one is we talk about the interstitial diffusing atom, and the second one will be the substitutional atom. And you can write down the flux can be expressed like the diffusivity and the driving force here, and substitutional part is because there's pure metal, so it's very difficult to label the diffusing atom. So here, in order to know the JA, we use by understanding or calculate the JV, then we can get the JA. And JV is much easier, right? Because you can use some material analyze tool to know the concentration of vacancy, the mobility of vacancy, and also the driving force for the vacancy. You can either use the TM, SEM, or SPM. Then you can have some idea about the vacancy, the information about the vacancy. And next, we are going to give you some example to demonstrate the importance of the electromigration. And the first one would be the Bletch effect, and the second one would be a current clouding. Both of these will happen in the connecting line in the IC chip.